Welcome, fellow cosmic detectives, to a journey into the deepest, darkest corners of the universe. We're talking about the cosmic voids, those vast, seemingly empty spaces between galaxy clusters that make up most of the cosmos. But are they truly empty? Scientists are discovering that these voids might be hiding some of the universe's most puzzling secrets. Get ready to have your mind expanded as we explore 25 unexplained phenomena lurking within the cosmic web's voids. From strange energy fields to phantom galaxies, these mysteries challenge our current understanding of everything. One of the most compelling puzzles we've found hiding in these voids is something astronomers call the cold spot. Imagine peering back to the very edge of the observable universe, to the faint afterglow of the Big Bang known as the cosmic microwave background. Scientists expect this background radiation to be pretty uniform, with only tiny variations reflecting the early universe. But nestled within a void, there's a huge area that's noticeably colder than it should be. This cold spot is bigger and chillier than our best models of the cosmos can easily explain. So, what's chilling down this vast patch of space? One idea is that it's simply an absolutely massive supervoid, a region even emptier than average, where light traveling through it gets stretched and appears colder. Another more mind-bending possibility is that the cold spot is a relic, maybe even an imprint, from a time when our universe potentially interacted with another, perhaps through a cosmic bubble collision. Moving from one large-scale mystery to another, consider something equally strange: the dark flow. Imagine not just one galaxy, but massive clusters of galaxies, all moving together in the same general direction. Scientists observing these colossal structures have detected a consistent overall motion, a kind of cosmic current heading towards a particular area of the sky. This unexplained movement, dubbed dark flow, is incredibly puzzling because it appears to be influenced by something completely outside the visible universe, beyond what we can currently see or measure. This suggests there might be immense, unseen concentrations of mass pulling on everything, structures on scales far grander than anything we've mapped so far. Could this collective galactic drift be evidence of influences from beyond our cosmic horizon? Moving from the large-scale movements of galaxies to the incredibly distant and powerful, we find another cosmic riddle: the perplexing alignment of quasars. These aren't just any celestial objects. Quasars are the brilliantly luminous cores of early galaxies, powered by supermassive black holes gobbling up matter. They sit billions of light-years away, effectively giving us a peek into the universe's distant past. What's baffling astronomers is that these incredibly bright beacons, scattered across the vast emptiness of the voids, don't appear to be oriented randomly. Instead, many of them seem to be lined up along the same axis, extending over truly enormous distances, far larger than individual galaxy clusters. This striking cosmic arrangement flies in the face of what we expect from the standard picture of the universe. A picture that says, on the grandest scales, everything should look pretty much the same in every direction, scattered without any preferred orientation. So, what invisible influence could possibly be reaching across billions of light-years, imposing this kind of grand-scale order on the most energetic objects in the universe? Delving deeper into the vastness of these voids brings us face to face with perhaps the biggest cosmic enigma of all: dark energy. Scientists widely agree that this mysterious force is responsible for the fact that the universe isn't just expanding, it's expanding at an ever-increasing rate. Think of it like an invisible anti-gravity pushing everything apart. While we know dark energy is out there, its true nature is still completely unknown. Now, because voids are such incredibly low-density regions, practically devoid of matter, they should, in theory, be the places where dark energy's influence is most dominant and easiest to study. This raises a crucial question: does the density of dark energy vary throughout the universe? Is there more of it, or does it behave differently within these vast empty voids compared to areas where galaxies and clusters are packed tightly together? Studying how voids grow and evolve could provide vital clues about dark energy's properties and how it interacts with the rest of the cosmos. Unraveling this could fundamentally change our understanding of the universe's ultimate fate. Now, shifting our gaze from the mysterious dark energy that fills these voids, let's consider another cosmic messenger, gravitational waves. We've become familiar with the powerful ripples in space-time generated by dramatic events like black holes colliding or neutron stars merging, usually happening in the more crowded parts of the universe where matter is abundant. But what about the vast emptiness of the voids? Could the sheer scale and subtle dynamics within the cosmic web itself, including the growth and evolution of these immense empty spaces, be generating weaker yet potentially detectable gravitational waves? Imagine faint whispers of space-time curvature rippling outwards from the very structure of the cosmos on its largest scales. Detecting such subtle gravitational signals, perhaps at extremely low frequencies, could offer a completely new way to probe the large-scale structure of the universe and how it has evolved over billions of years. It's a tantalizing possibility that the quiet expansion and subtle structural shifts within the voids might be leaving their own unique gravitational footprint on the fabric of reality. Shifting gears from the ripples of space-time, let's talk about something seemingly more ordinary, but no less mysterious: normal matter. By normal matter, we mean the stuff you, me, stars, and galaxies are made of: protons and neutrons, which scientists call baryons. Now, according to our best computer simulations of how the universe evolved, a huge chunk of this baryonic matter shouldn't be clumped up in galaxies and clusters. It should be spread out in the vast spaces between them, forming threads and filaments of very hot, thin gas known as the warm-hot intergalactic medium, or WIM. The cosmic voids, being the largest and emptiest regions, ought to contain a significant amount of this elusive WIM. The problem is, despite extensive searching, we've had a devil of a time actually finding and detecting this missing baryonic matter in the voids. It's like a cosmic game of hide and seek, and the WIM is winning. Where is all this expected normal matter hiding? Is it so diffuse and hot that it's practically invisible to our instruments? Or is it in some exotic state we haven't fully anticipated? Pinpointing and studying this missing matter is crucial, because finding it would help confirm our models of cosmic evolution and fully account for all the ingredients the universe is made of. You know, for regions officially defined by their lack of galaxies, the cosmic voids are turning out to be surprisingly unempty. We fully expected to find these vast stretches of the universe to be essentially barren, but telescope observations keep revealing something unexpected. Galaxies actually live inside some of them. Not clusters, mind you, but isolated, sometimes even surprisingly large, individual galaxies dotted here and there within the sparse cosmic fabric of the void. It's like finding a bustling town marooned in the middle of a vast, empty desert. How do these galactic islands form and grow in such a profoundly undersupplied environment? Building a galaxy requires enormous amounts of gas and dust to collapse and ignite stars over billions of years. In the denser parts of the cosmic web, galaxies have the gravity of their neighbors and the infalling streams of matter from surrounding filaments to help them gather the building blocks they need. But in the voids, matter is incredibly scarce. It's hard to imagine enough material being available to form and sustain a galaxy, let alone one that appears relatively normal. Their very existence challenges our models of galaxy formation and evolution, suggesting there might be processes at play in these low-density regions that we don't yet fully understand. So how exactly do these lone galaxies manage to exist in the cosmic wilderness? The traditional picture of galaxy formation involves vast clouds of gas and dark matter collapsing within dense knots in the cosmic web, drawn together by gravity. But in the voids, with so little material around, that standard process seems incredibly inefficient, almost impossible. One leading idea is that void galaxies might be leftovers from an earlier time in the universe, perhaps forming when the cosmos was smaller and denser. Even the voids weren't quite so empty. Perhaps they coalesced from slightly denser pockets within the primordial soup before the large-scale cosmic structure really solidified and pulled most of the matter into filaments and clusters. Another intriguing possibility is that these void dwellers might have formed through some sort of cosmic luck, accumulating just enough matter over billions of years from the incredibly sparse surroundings to slowly build up into a galaxy-sized structure. Think of it as patiently gathering specks of dust in an otherwise empty room. Their survival is also a puzzle. Without the strong gravitational tides from neighboring galaxies that can strip away gas and disrupt star formation, maybe void galaxies lose their star-forming fuel more slowly, allowing them to age gracefully in isolation. It's a fascinating puzzle that forces us to reconsider the minimum requirements for building a galaxy. So, we've explored how inexplicable galaxies might reside in these seemingly desolate regions, but that begs a bigger question. Are voids just passive absences of stuff, or do they actively sculpt the universe around them? It turns out these vast empty bubbles are far more than just blank spaces. They are powerful agents in the grand cosmic drama of structure formation. Think of it like this, where the cosmic web has its dense knots and filaments pulling matter together to form galaxy clusters. The voids are the expansive spaces pushing things apart. As the universe expands, the relatively low density inside the voids means their expansion is less resisted by gravity compared to the denser regions. This faster expansion within the voids effectively stretches and pulls on the surrounding matter, drawing it towards the denser filaments and knots. So, instead of just being areas that matter avoids, voids are actively contributing to the growth of the cosmic web structure, like negative space in a sculpture that defines the form of the positive elements. They aren't just absences, they are dynamic parts of the universal architecture. Now consider a force we're all familiar with here on Earth: magnetism. It might seem strange to think of magnetic fields existing on the truly colossal scales of cosmic voids, but evidence is mounting that these fields are indeed present, silently shaping the universe in ways we're only beginning to understand. Detecting these vast cosmic magnets is incredibly difficult. We can't just wave a compass in a void. Instead, scientists look for subtle clues, like the way light from distant objects or radio waves from cosmic sources gets affected as it travels through these empty spaces. The polarization of light, for instance, can be rotated if it passes through a magnetic field. These observations hint that weak but incredibly extended magnetic fields permeate the voids. This raises fundamental questions. Where did these large-scale magnetic fields come from in the first place? Were they generated in the very early universe, perhaps shortly after the Big Bang, and then simply stretched and diluted by the cosmos's expansion? Or are they somehow created or amplified by the subtle movements of matter within the voids themselves? Even though there's so little of it, understanding the origin and strength of these magnetic fields is crucial because they could be influencing how matter, even the sparse matter in voids, moves around and how the cosmic web itself forms and evolves. They might be another invisible thread in the vast tapestry of the universe. Now, let's consider some of the most energetic particles zipping through the cosmos: cosmic rays. These are atomic nuclei, or sometimes just single protons, traveling at nearly the speed of light, carrying immense amounts of energy. Scientists have long believed that the most powerful cosmic rays are forged in the universe's most violent crucibles, like supernova explosions, colliding neutron stars, or the active cores of galaxies where material is being violently ejected from supermassive black holes. These are all high-density environments, packed with the ingredients and forces needed to accelerate particles to such extreme speeds. But what if, just maybe, some of these ultra-high energy particles are actually getting their incredible boost within the voids? It seems counterintuitive given how empty these regions are. However, the sheer scale of voids and the influence of those weak, extended magnetic fields we just discussed could potentially act as colossal particle accelerators over vast distances. We're talking about the possibility of mechanisms we haven't even fully theorized yet, where particles gain energy from interacting with the subtle structures and fields present within these immense empty spaces, accelerating them to incredible speeds before they finally reach our detectors on Earth. This idea challenges our current understanding of where the most powerful particles in the universe come from. Stepping back from the individual mysteries within the voids, let's consider something truly mind-boggling: the existence of incredibly gigantic structures in the universe, so large they dwarf galaxy clusters and span billions of light years, incorporating these very voids and the dense filaments between them. Think of structures like the Sloan Great Wall, a cosmic arrangement of galaxies extending over 1 billion light years. The sheer scale of these formations presents a significant puzzle. According to our current understanding of cosmology, based on gravity as the primary force shaping the universe since the Big Bang, there simply hasn't been enough time, just 13.8 billion years, for gravity alone to pull together enough matter to form structures of this immense size. Light, the fastest thing in the universe, would take 1 billion years to cross the Sloan Great Wall, meaning its constituent parts couldn't have influenced each other through gravity over that timescale within the age of the universe. This disconnect between the scale of observed structures and the time available for their formation raises fundamental questions. Are there other forces beyond just gravity and dark energy that are playing a role in sculpting the cosmic web on these truly grand scales? Could the dynamic interplay between voids and filaments, or perhaps something even more exotic, be contributing to the assembly of these cosmic behemoths in ways we haven't fully grasped? While the voids are the vast empty arenas of the cosmos, they are defined and bordered by the dense, thread-like highways of the cosmic web, the filaments. These cosmic threads are where the vast majority of galaxies, including our own Milky Way, are found, pulled together by gravity into these long, intricate structures. Think of the universe as a giant sponge, with the voids as the holes and the filaments as the material that makes up the sponge itself. But exactly how did this incredibly complex filamentary network form and evolve over billions of years? We understand the basic principle: gravity draws matter together into the denser regions. However, the incredibly precise, interconnected patterns we observe, with filaments wrapping around voids like a cosmic scaffold, are still full of unanswered questions. The voids aren't just passive gaps; their expansion puts outward pressure, helping to channel matter into these surrounding filaments. It's a dynamic dance between the empty and dense regions, and unraveling the intricate details of this cosmic choreography, how filaments merge, how matter flows along them, and how the voids influence their shape, is key to painting a complete picture of the universe's structure on the grandest scales. Now, let's consider a truly exotic possibility lurking in the voids of primordial black holes. Unlike the black holes formed from the collapse of massive stars, these hypothetical objects would have condensed directly from the incredibly dense conditions of the very early universe, perhaps just moments after the Big Bang. They could range in size from microscopic, about the mass of an asteroid, all the way up to many times the mass of our Sun. Because they formed before galaxies and stars even existed, they should, in theory, be scattered throughout the cosmos, including in the vast empty spaces of the voids. The intriguing part is this: even though voids are low-density regions, the gravitational pull of a primordial black hole, even a relatively small one, could significantly influence the sparse matter around it. While we haven't directly detected primordial black holes, their potential gravitational influence within the voids could subtly affect the distribution of the sparse gas, or even contribute to the formation of those rare void galaxies we talked about earlier? Could some of the unexplained gravitational anomalies or motions observed in these empty regions be the silent signature of these ancient, unseen cosmic remnants? It's a fascinating thought that these vast empty spaces might be hiding some of the oldest and most mysterious objects in the universe. Now, let's turn our attention to the invisible foundation of the universe, dark matter. This mysterious substance doesn't emit, absorb, or reflect light, making it incredibly difficult to detect directly. Yet we know it's there because of its gravitational influence on visible matter and light. In fact, dark matter outweighs normal matter by about 6-to-1, making it the dominant form of matter in the cosmos. This means that the vast structure of the cosmic web, with its dense filaments and expansive voids, is primarily shaped by the gravitational pull of dark matter. Think of dark matter as the invisible scaffolding upon which the visible universe is built. In the voids where normal matter is incredibly sparse, dark matter's influence should, in theory, be even more pronounced in terms of defining the region's gravitational landscape. How does dark matter distribute itself in these low-density environments? Does it cluster weakly, or is it spread out more uniformly than in the dense filaments? Understanding how dark matter behaves in the voids is crucial because its subtle gravitational effects could be contributing to some of the other unexplained phenomena we've discussed, like the formation of void galaxies or even influencing the subtle motions within these seemingly empty regions. Now let's venture into perhaps the most speculative and exciting territory of all: the possibility of life, even extraterrestrial life, existing within these vast cosmic voids. At first glance, it seems almost impossible, right? Voids are characterized by their extreme emptiness, a profound lack of the matter and energy we typically associate with nurturing life. We think of life needing planets orbiting stars, and stars and planets are incredibly rare within these regions. However, the universe has a knack for surprising us, and the concept of life in the voids, while highly speculative, isn't entirely dismissed. It's anchored in the existence of those few, isolated void galaxies and the even rarer individual stars that might reside there. Could a planet orbiting one of these lonely stars harbor life, insulated from the hustle and bustle of the crowded cosmic web? Perhaps life forms could exist in ways we haven't even imagined, adapted to the unique conditions of low density and minimal external influence. While it's a long shot, the sheer scale of the voids means that even extremely rare occurrences might add up to something significant across billions of cubic light years. It remains a captivating unknown, a question that pushes the boundaries of our imagination about where life could potentially arise in the cosmos. Shifting from the possibility of life in these desolate places, let's talk about how voids leave their fingerprints on the oldest light in the universe. We're talking about that faint afterglow of the Big Bang, the cosmic microwave background, or CMB. While generally smooth, the CMB has tiny temperature variations, hot and cold spots called anisotropies. These aren't random, they're like a snapshot of the universe when it was just a baby, about 380,000 years old. Now, as this ancient light travels across billions of years to reach our telescopes, it passes through the cosmic web we see today: the filaments, clusters, and of course the vast voids. The immense gravitational pull of the large-scale structure it encounters subtly affects the energy of the CMB photons. Light passing through dense regions gets a slight energy boost, while light traversing the underdense voids loses a tiny bit of energy. It's like rolling a ball over a bumpy surface. It speeds up going downhill and slows down going uphill. These subtle changes as the light navigates the gravitational landscape of the cosmos leave a unique imprint on the CMB anisotropies. By precisely measuring these tiny temperature fluctuations, scientists can glean incredible information about the large-scale structure the light traveled through, including the properties of the voids. Studying how voids affect the CMB isn't just a scientific curiosity. It's a powerful tool for testing our fundamental cosmological models, the mathematical frameworks we use to describe the universe and its evolution. Do our models accurately predict the effect of voids on the CMB? Any discrepancies could point to new physics or a deeper understanding of the universe's large-scale architecture. Because voids represent the most extreme examples of large-scale structure in the universe, incredibly dilute and expansive, they offer a unique laboratory for testing the fundamental laws of physics, potentially even revealing cracks in our current understanding. Think about it, our standard model of particle physics and general relativity, our best theory of gravity, were largely developed and tested in relatively normal conditions here on Earth within our solar system and observing galaxies and clusters where matter is dense. But do these laws hold up equally well in the near vacuum of the voids and over the truly immense distances that define them? Some scientists speculate that the weak gravitational fields and extremely low densities could be the perfect environment to see subtle effects or deviations that are masked elsewhere. For instance, do we need to modify our understanding of gravity itself to fully explain the dynamics and formation of voids and the structures around them? Or could observations of how the sparse matter and dark matter are distributed within voids, or how light travels through them, provide clues about the nature of dark energy, dark matter, or perhaps even reveal entirely new types of particles or fields that only manifest themselves under these extreme conditions? The quiescent, low-density environment might just be the place where the universe whispers secrets about physics beyond what we currently know, secrets that are drowned out by the cosmic noise in more crowded regions. So, we've thought about dark matter in the voids themselves, but let's consider its influence closer to home within galaxies. You see, one of the major pieces of evidence for dark matter comes from how galaxies spin. Stars and gas clouds in the outer parts of galaxies orbit much faster than they should based on the gravity of the visible matter alone. This discrepancy led to the idea that galaxies are embedded within much larger, invisible halos of dark matter, whose gravitational pull keeps everything spinning smoothly. Now, while the main action is inside the galaxy's dark matter halo, the structure of the cosmic web around that galaxy, including the proximity of surrounding voids, might play a subtle role. The gravitational pull from the denser filaments and the relative lack of pull from nearby voids could subtly shape the dark matter halo of a galaxy and, in turn, influence its rotation curve. It's like the galaxy is sitting in a gravitational landscape carved out by the large-scale structure, and that landscape might have a minor but measurable effect on its internal spin. Quantifying this influence is tricky business, as it's a small effect on top of the dominant dark matter within the halo, but it's another way the universe's largest empty spaces might be influencing the structures within them in ways we are still trying to figure out. Now, let's switch gears and talk about some of the most enigmatic signals zipping across the cosmos, fast radio bursts or FRB. Imagine incredibly intense flashes of radio waves lasting for mere milliseconds but packing more energy than the sun emits in a day. These are not your average radio signals, they're powerful, fleeting, and their origins are a profound mystery. While some FRBs have been traced back to galaxies, sometimes even repeating bursts coming from the same source, others seem to defy explanation, appearing to originate from seemingly empty stretches of space. Could some of these signals be coming from those vast, desolate voids we've been discussing? Or perhaps even from regions far beyond the observable cosmic web itself? If an FRB were to originate within a void, how would such a powerful event occur in a region so devoid of matter and energy? The conditions required to generate such a burst of energy are thought to be extreme, perhaps involving highly magnetized neutron stars called magnetars or other exotic compact objects. The detection of FRBs without a clear galactic host seemingly floating in the emptiness challenges our understanding of where these cosmic fireworks can ignite. It suggests there might be powerful astrophysical phenomena occurring in the universe's most desolate regions, or perhaps these signals are traveling through vast voids and arriving from sources so distant they appear to be in empty space. It's a cosmic riddle with no easy answer, leaving scientists scratching their heads about the true nature and location of these mysterious radio flashes. Moving on to potentially even stranger inhabitants of the voids, imagine cosmic strings. These aren't strings like you'd use to tie a shoelace. They are entirely hypothetical, one-dimensional defects in the fabric of space-time itself, relics thought to have been formed in the incredibly energetic and chaotic moments just after the Big Bang. Think of them like cracks or wrinkles that got frozen into existence as the universe cooled and expanded. Because they are theorized to be incredibly massive and thin, they shouldn't clump together in the same way as normal matter or dark matter. Instead, they could be stretched out across the cosmos, potentially running right through the vast emptiness of the voids. While they are incredibly difficult to detect directly, the potential gravitational effects of these cosmic strings, or perhaps other subtle signatures they might leave behind, could be lurking in observations of the voids. They could subtly bend the light from distant objects, leave telltale patterns in the cosmic microwave background radiation, or even generate their own unique form of gravitational waves. Detecting evidence of cosmic strings, especially in the relatively undisturbed environment of a void, would be a monumental discovery, providing direct proof of exotic physics from the universe's earliest moments and offering a glimpse into the fundamental nature of reality itself. Let's shift our gaze to something else entirely, the Lyman Alpha Forest. This isn't a real forest, of course, but a complex pattern observed in the light from those incredibly distant, bright quasars we talked about earlier. As that light travels across billions of light years towards us, it passes through vast clouds of mostly neutral hydrogen gas that are scattered throughout the cosmic web, including within the voids. Each time the light encounters one of these hydrogen clouds, it gets absorbed at a very specific wavelength, creating a dark absorption line in the quasar's spectrum, kind of like missing notes in a musical scale. Because these clouds are spread out at different distances, each absorption line corresponds to a different cloud, creating a complex pattern of lines that scientists call the Lyman Alpha Forest. Now, the density and distribution of the hydrogen gas in these clouds directly relate to the density and distribution of matter in the universe itself. By carefully analyzing the structure and characteristics of this forest, how many lines there are, how dark they are, and where they appear in the spectrum, astronomers can actually probe the amount and arrangement of the diffuse hydrogen gas within the voids. Think of the Lyman Alpha Forest as a ghostly map of the intervening cosmic web, revealing details about the empty spaces that the light has traversed. Studying this cosmic fingerprint gives us valuable insights into just how empty the voids truly are and how the sparse matter within them is distributed. Think of the cosmic web as a living, evolving structure, not just a static snapshot. And just like cells dividing or rivers flowing, the voids within this web aren't staying put. Over billions of years of cosmic history, these vast empty bubbles have been growing, expanding as the universe expands, and they haven't always remained separate. Scientists are finding evidence that voids actually merge with each other, like two bubbles combining into a larger one. This process of void mergers is a critical part of how the large-scale structure of the cosmos evolves, and understanding the dynamics of these mergers, how they influence the matter around them, how they change the shape of the cosmic web, and what they tell us about the universe's history is an area of intense, ongoing research, still packed with unanswered questions. As the universe continues its accelerating expansion, a phenomenon driven by the mysterious force of dark energy, the cosmic voids are poised to become even more dominant features on the universal landscape. Think of these vast empty spaces not just as they are now, but how they will be billions of years into the future. our current understanding suggests that as everything recedes from everything else, the relatively low density of matter within the voids means they expand even faster than the denser parts of the cosmic web. This leads to a fascinating long-term projection. These cosmic bubbles will grow larger and emptier, pushing the filaments and clusters of galaxies further and further apart. What are the long-term implications of this? Will the voids eventually assert such dominance that they essentially tear apart the existing cosmic web, isolating galaxies or even galaxy clusters within ever-expanding pockets of nothingness? It's a future where the universe's large-scale structure becomes increasingly defined by its emptiness, a chilling prospect that forces us to contemplate the ultimate fate of the cosmos. Now let's venture into the realm of pure cosmic speculation, a thought experiment that pushes the boundaries of what we consider possible. Could advanced civilizations actually choose to live in the cosmic voids? Imagine a civilization that perhaps sees the dense, crowded parts of the universe, the galaxy clusters and filaments, as loud, chaotic, and potentially dangerous places. Perhaps they seek solitude, stability, or even freedom from the intense gravitational pulls and frequent galactic collisions that occur in the cosmic web's denser knots. What if they actively ventured into the voids, not because they were forced out of their original homes, but because they saw the immense, quiet emptiness as an opportunity? Living in a void would present incredible challenges, certainly. Access to resources like heavy elements, the building blocks of planets and technology, would be incredibly scarce. Generating and maintaining energy might require harvesting the faint, diffuse cosmic background radiation, or somehow tapping into the subtle energy of the void itself. Communication with other potential civilizations, either within the void or in the distant galaxies, would be a monumental task requiring vast amounts of power to send signals across such immense distances. Yet, the voids also offer potential advantages: relative freedom from gravitational tides, fewer stellar encounters or supernova threats, and perhaps even a clearer view of the distant universe without the obscuring dust and gas of dense galactic environments. It's a concept that sounds like science fiction, absolutely, but it's a question that arises when we contemplate the sheer vastness and varied environments of the cosmos and the boundless potential for life to adapt to the most extreme conditions. After exploring all these intriguing possibilities, from cosmic strings to the potential for life, we arrive at perhaps the most fundamental puzzle about the cosmic voids: their very emptiness. We've discussed how they're mostly devoid of normal matter, those building blocks of stars and galaxies that make up the familiar universe, and we've touched on the idea that they are permeated by dark energy, the force driving cosmic expansion. But what if this emptiness isn't just a simple lack of stuff? What if there's something else, something entirely unexpected, lurking in these vast cosmic gulfs that our current physics hasn't even imagined? Could these voids be truly empty, containing nothing but the fundamental fields of physics and the pervasive dark energy? Or is there a deeper layer of reality within them, a hidden structure or substance waiting to be discovered? This ultimate mystery of the void's profound emptiness challenges our understanding of the absolute minimum ingredients required to fill the universe and pushes us to question what nothing truly means on the grandest cosmic scales. Remember that curious cold spot in the cosmic microwave background we talked about, the one that's bigger and colder than it should be according to our standard models? Well, besides the supervoid explanation, scientists have come up with some truly mind-bending alternative ideas that venture into the realm of exotic physics and the universe's earliest moments. What if the cold spot isn't just an unusually empty patch of space, but a sign of something far stranger, something left over from the universe's infancy? One fascinating possibility is that it's the imprint of a texture, a type of topological defect predicted by some theories about the universe's structure and evolution. Think of it like a knot or a twist in the fabric of spacetime itself, left behind during a rapid phase transition in the baby universe, maybe like how ice crystals form in freezing water. These textures, if they exist, could have subtle gravitational or energy imprints on the surrounding cosmos, potentially manifesting as large-scale temperature anomalies like the cold spot. Another related idea is that it could be a relic from a different kind of phase transition altogether, a moment when the universe underwent a dramatic shift in its fundamental properties, leaving behind a localized scar that cooled a vast region of space. These are highly speculative ideas requiring physics beyond our current standard model, but the persistence of the cold spot anomaly keeps them firmly within the realm of serious scientific inquiry. Could this vast, cold region in the void be a window into the universe's deepest past and the fundamental forces that shaped it? It's a cosmic riddle that continues to push the boundaries of our imagination. Remember that mysterious dark flow we discussed earlier, the one hinting that massive galaxy clusters are all being subtly pulled in the same direction by something beyond our visible universe? Well, the puzzle of its origin is far from solved, and scientists are employing a range of clever observational techniques to try and pinpoint its source. One primary method involves measuring the peculiar velocities of galaxy clusters, essentially figuring out how fast they're moving relative to the overall expansion of the universe. By mapping these movements across vast cosmic distances, astronomers can try to trace back the gravitational influence causing this collective flow. Think of it like watching a huge fleet of ships all being drawn towards a specific point on the horizon you can't quite see. Researchers use data from large galaxy surveys and the faint distortions in the cosmic microwave background caused by the gravitational pull of large structures to get these measurements. However, this is incredibly challenging work. Measuring the precise distances and speeds of objects billions of light years away is difficult, and the signal of the dark flow is subtle, easily masked by other factors influencing galactic motion. There are also limitations to how far back and how wide we can map these movements with current telescopes. We're essentially trying to understand an enormous cosmic tug of war based on observing one side of the rope. Yet, the hope is that future astronomical missions and more sensitive instruments, perhaps designed specifically to map large-scale cosmic flows or even detect the gravitational signature of structures far beyond our current view, might finally reveal the unseen hand guiding this cosmic current. Let's return to those unexpected inhabitants of the cosmic voids, the void galaxies, and peer even closer, analyzing their fundamental makeup. What secrets can the very elements they contain reveal about their lonely journeys and the strange cosmic environments they call home? Scientists study the light emitted by these galaxies, particularly the spectral lines corresponding to different elements, to determine their chemical composition. This composition is a sort of cosmic fossil record. It tells us about the history of star formation within the galaxy. Stars are the universe's element factories, forging heavier elements like carbon, oxygen, and iron from lighter ones like hydrogen and helium. When stars die, they release these elements back into the surrounding gas, enriching the galaxy's chemical mix. Now, if void galaxies formed and evolved in isolation, cut off from the influx of fresh gas and metals that denser regions provide, you might expect them to have a different chemical signature than their crowded counterparts in filaments and clusters. Maybe they'd have lower abundances of heavier elements, reflecting a slower or less vigorous history of star formation. Analyzing these chemical fingerprints helps us piece together their formation story and understand if growing up in a void leaves an indelible mark on a galaxy's elemental recipe. And there you have it, 25 unexplained phenomena lurking within the cosmic web's voids that continue to baffle scientists and fuel our curiosity about the universe. From the chilling enigma of the cold spot in the cosmic microwave background to the mysterious pull of the dark flow and the surprising presence of galaxies where they shouldn't be, These cosmic enigmas are powerful reminders of just how much we still have to learn about the vast cosmos we inhabit. They push the boundaries of our current understanding and keep scientists scrambling to find answers. What do you find to be the most intriguing mystery of the voids? Is it the idea of primordial black holes scattered through the emptiness, the possibility of undetected cosmic magnetic fields, or something else entirely? We'd love to hear your thoughts and theories in the comments below. Don't forget to give this video a thumbs up if you enjoyed this journey into the unknown, and subscribe to the channel for more cosmic explorations and dives into the universe's deepest secrets.